I'm going to go ahead and just briefly kick off and say good morning, everybody. Thanks for being here in class on time. We really appreciate that, getting started on time at 9 a.m. And today we are delighted to have a representative, Mr. Alex Austin from JPL, so NASA's Jet Propulsion Laboratory. Alex, if I have your title correct from LinkedIn, Alex, correct me if I get this wrong, is the lead of JPL's concurrent engineering design team and is today here as a representative for the JPL Innovation Foundry, which is an industry-wide, highly respected, just an amazing concentration of new mission ideas and formulation, and some of the proposals that come out of JPL are standard setting for the rest of us. So it's really fantastic to have Alex here today. And with that, Alex, please add any other details if I've missed something you'd like to share, and we'll pass the baton to you to do your presentation for today.
Okay, thank you so much. Let me see if I can share my screen here. And so is this coming through for you?
It is.
Great, okay. And so first of all, I'm in Los Angeles. It is a little bit early and I just woke up. So if I sound a little bit groggy, hopefully that gets better in the next half hour or so. But thank you so much for the introduction. Yes, my name is Alex. I am a systems engineer at the Jet Propulsion Laboratory. I lead one of our concurrent engineering teams within the Innovation Foundry. We have a couple of different teams that I'll talk to you about today. The team that I lead specifically is what we call Team XC, which is focused on small missions from CubeSats up to spacecraft of a couple hundred kilograms. But I'll be giving you a more general talk about all of our teams within the Innovation Foundry and how we mature concepts for space missions and for technologies at JPL. I wish they had a class like this when I was in school. I've been at JPL for about 5 years. So I did not go through virtual classes as you all are doing now, but I'm not too far out of school. So it's quite an honor to have the opportunity to speak to you all and give you some of my perspectives, and I'm happy to answer all of your questions as well. Okay, so with that, let me just get into it, and feel free to stop me if you have questions. And I'm looking forward to the breakout groups as well as we get into that. So if you're not familiar with the Jet Propulsion Laboratory, we are one of the NASA centers, but we're a little bit unique to the other NASA centers because we're actually a division of the California Institute of Technology. So we're what's called a federally funded research and development center, which is just kind of a nice long acronym that we like at NASA. But we focus mostly on robotic exploration. You probably know JPL best for planetary science missions like the recent Perseverance rover and Ingenuity helicopter. But we also do a lot of work with earth science and astrophysics, as well as a lot of new space technologies. These are some of my favorite missions that are currently being worked on right now. We have about 6,000 employees at our facility in Southern California. The laboratory's been around for a long time. It's was responsible for the Explorer 1 satellite, way back when our first US satellite. So it's a very interesting place to work. I kind of sit at the beginning of projects in the formulation area. And again, that's really what the Innovation Foundry focuses on is what are the missions that we'll be doing in the next 5 to 100 years, depending on the study. We can get pretty futuristic or we can get pretty realistic, depending on where the mission's going to be going in terms of the timeline. So a little bit more about the Innovation Foundry. So we're a group at JPL that coordinates all of JPL's mission proposals and formulation activities. We have a couple different teams within the Foundry. And today I'll be focusing mostly on what we do in what we call the A team, which is the architecture team. And the A team, those are kind of like workshop-like activities where we focus on kind of the big picture, what's your idea, exploring the trade space. And then eventually that goes to Team X and Team XC, where we actually kind of put some real numbers to it and put together a point design. I'll touch on all these teams, but again, mostly focusing on the A team. And here you'll see, so Team XC is the team that I lead, but we have leads for each of these teams, and we all work really closely together because ultimately it's our job to help our concepts, walk through the process of formulation, and they pass from one team to the next depending on what they need. Eventually, once you get a design, you go to a proposal team, and that's a pretty big effort to actually write up a full mission proposal to NASA. Right now, we're working very hard on our discovery missions, which are planetary science missions. Just to give you an example, that's kind of our focus right now. But depending on the year and the specific proposal call that NASA has out, we are oftentimes doing anywhere from 25 to 50 proposals for different types of missions. So we keep pretty busy. So I don't really, this is a very NASA diagram. It's kind of boring, but it is very important. And this is just to give you a little bit of context about what is the life cycle of a NASA mission. You might have seen some of this before, but generally at NASA, we have two types of missions. We have what we call assigned missions. So these are missions that are directed by Congress. Something like the Artemis program would be an example of an assigned mission. Something like the Mars Perseverance rover is another example. And then we also have what we call competed missions. And competed missions are like the Discovery class mission that I just mentioned. Those are missions that organizations are able to put in proposals to NASA. And ultimately, NASA selects one or a couple for implementation. And the life cycle for these types of missions has similarities, but also differences. You'll notice that they go through the same main phases. So we have pre-phase A is formulation concept studies. They go to then phase A, which is where you develop the concept further, including any new technologies. Phase B is where you put together your preliminary design and potentially complete some technology development work. And then phase C is really getting into the implementation portion, where you're actually putting together the final design, building the spacecraft, launching it. And then phase E is where you're actually operating it. And there's these decision reviews along the way. And I put this in because I know that you folks are working towards a few reviews as part of your class here, where you have, a PDR that gets you into phase C, a CDR, which gets you into phase D. And now in the end, these are all really important reviews. And this whole process for a mission, for a discovery mission from initial concept through to launch, generally can take on the order of maybe 6 to 8 years or so. So it's quite a process, especially for these very big space missions. So the Foundry really focuses up here in phase A and phase B. And I know that's really what you're focusing on mostly for this class as well. Although it's pretty cool. You're working on some payloads and things too. So you're even kind of getting into the later phases, which is awesome. But I'll focus up here on the formulation activities for today. Okay, so that was a really kind of boring NASA diagram. This one's a little bit more fun. So at JPL, to help our concepts kind of walk through the process of formulation, we realized that we needed something to provide them some concrete steps. And from that came the concept of a concept maturity level. This is similar to a technology readiness level, a TRL, which you might be familiar with. And really, it's just a way to kind of visualize, how do I go from my initial idea all the way to, a baseline project that holds together and is ready for implementation. And you'll see that you walk through from 1 through 8, all the way from, the cocktail napkin, I've got this great inspiration, to checking the initial feasibility, does it have any chance of working, exploring the trade space, really opening up the possibilities, trying to make sure you've taken a look at all the different options, ultimately converging those options down to a specific point design, and then really putting the details on to get your concept put together for your PDR. And in NASA speak, really those boundaries come up at CMLs 5 and 8. So CML 5 would be that boundary from, initial concept into initial design. And then CML8 is where the innovation foundry hands off the concept at JPL. There's a PDR. We hand it off to the implementation side of the laboratory. And then it gets implemented by the team that we have that actually, ends up putting all the pieces together to launch the mission. And what we realized really is that it's important when considering these CMLs, these concept maturity levels, and maturing your concept, to not just dive into one aspect of it. A lot of times it's very easy just to dive into, let's say, the technical implementation, but miss a lot of the other major pieces that make a good concept. So you've got to look at the implementation, but you've also always got to be looking at what's your science. In our case, it's mostly science missions. But for something like you're working on, it might not be science, but it might be technology objectives. But those are going to go hand in hand. What do you want to do and how do you want to do it? But beyond that, you also need to always consider the cost of your mission. We found that with enough money, you can do just about anything, but normally money becomes the biggest driver of actually being able to get something done. So you've always got to be thinking about that. And finally, there's this overarching thing that you always want to be thinking about, and that's the strategy. A lot of what we do at early concept levels ends up kind of looking a lot like business development. We're scientists, we're engineers, but especially with those competed missions, you've got to convince NASA that your mission's worth flying. So there's a big strategy aspect to it too, of how do you actually get your concept out there. So it's really important when you're maturing your concept to think about all these things at the same time, because they're all going to feed off each other. So today I'll focus on CMLs 1 through 3. We don't really have time to go through all of them, but I know that's kind of where you are right now in your concept development. So hopefully that's helpful. I'm not going to read through this chart, but I put this in because you're welcome to have the slides, so you can take a look at some more specific examples of what it means to be at each CML. But I think I talked through most of it with the graphic, so I'm just going to skip over here in the interest of time. Okay, so CML 1 through 3 at JPL, how do we actually do this? This is the A team. And the A team, it's a pretty fun place to be. I have a few pictures here from some of our studies. We have this room that we call left field because all the craziest ideas come out of left field. And we have this place, there's big whiteboards and Legos. And I mean, this is the place to really come up with ideas and explore what's the trade space. We get a team of experts together. Each study is a little bit different. There's generally a leadership team that helps to organize the study, but the participants are a little bit different each time. Depending on the mission, you might need a lunar expert or a Mars expert. You might need a rover expert or an orbiter expert. So we put the teams together, depending on what the study needs. But we get everyone together. We lock ourselves in a room, or in this case, because we're all remote, in a WebEx for the day. And we all talk and we all think about these problems and we all try to come up with the best solution. It's really, like I said, quite a fun team to work with, because you're allowed to be really innovative and try to come up with these, unique solutions to these problems. So I'm going to walk you through the CMLs and provide a little bit more of an explanation and also an example for 1 through 3 to hopefully help to give you a little bit more context for a lunar application. Okay, so CML1, this is the cocktail napkin. This is, what is my idea and what are the major components of it? And what we found is that actually there's a CML0, there's an inspiration for your idea. And generally that inspiration is one of the things that you see on the top part of the slide here, although the last one's an NA because it could really come from anywhere. Is there a new opportunity? Are there new science questions? Is there a new technology? Some new solution that makes it lower cost, that creates some inspiration for an idea. But really the point of this chart is to show that on the bottom boxes show everything you need for CML1. And the challenge is to go from any of those inspirations to all of the things for CML1. Oftentimes we see concept teams come through where they have a great new technology, but a new technology doesn't get a mission. what the challenge is to take your inspiration from that new technology and put together all the pieces that make a complete concept. And that's really what it takes to get to CML1, the complete cocktail napkin idea. So I think this is best illustrated with an example. So I have a lunar example. Obviously, one of the most exciting things about the current lunar program is the exploration of volatiles and water ice at the South Pole. So here's a kind of a timely example for you. Imagine the inspiration is that there's a new opportunity with the Artemis program that's going to enable more lunar exploration. There's new providers for payload delivery services that will allow us to get more mass to the moon. And that's going to enable the testing of these new hypotheses surrounding the existence of water ice as a resource for human exploration. Wow, that sounds pretty cool, right? But now, how do we actually take that inspiration and make a complete idea? So here's one example. If we think about the value proposition for NASA, what's our overall strategy? Well, we know NASA wants to conduct breakthrough science and enable human exploration. So they're probably going to really like the idea of exploring lunar volatiles because it supports key scientific objectives and resource utilization. Okay, so we think we have a strategy. What actually are our science questions? Well, there's the obvious one, what volatiles are present, but that's not really enough. Just go in there to see if there's something there probably isn't enough. So we need to dive a little bit deeper. What's their concentration? How could we access them? These are the types of questions that you want to come up with for a CML1 idea. The next thing is, well, how are we actually going to do this? What are going to be some of the key drivers on the engineering system? Well, we know that we want to do in situ measurements. We know that we want to explore over a diverse range and depth of areas. So we're going to need some kind of mobility system and ability to access the subsurface. How are we going to actually implement this? Well, we're going to take advantage of commercial lunar payload services, the CLIPS landers for delivery. But this rover is probably going to be pretty complicated. So we're going to give that rover to NASA because they have a lot of experience from our prior Mars rovers. Again, let's not forget about cost. What do we think? We're not trying to get down to the exact dollar number at this point, but how much do we think this would probably cost? And a lot of times we can look at analogies. So we know that the Spirit and Opportunity rovers on Mars were about $1 billion. Curiosity and Perseverance are about $2.5 billion. So this is probably a $1 billion class mission, kind of to frame our thinking. And finally, you've got to be able to put together some kind of 2-sentence pitch that really gets your concept across. In this case, you want to generally cover both why is it exciting and how are you going to do it. So for this mission, this lunar volatiles exploration mission will help NASA to make scientific discoveries and enable human exploration by mapping the concentration and composition of potential resources. And this will be because the payload delivery capabilities of CLIPS providers coupled with the NASA experience in successfully executing planetary rover missions. So that's an example of going from an inspiration to a complete idea. And it's really important not to skip this step and just stick with your inspiration, because once you've got your complete idea written out, it's going to help you as you move forward to always go back to some of these key components of it. Okay, so we've made it past CML1. We have a complete idea for this awesome Lunar Volatiles rover mission. Now we're going to go to CML2. So the CML2 is initial feasibility. This is actually demonstrating that this thing has a high likelihood of working. And again, you're going to see that I keep going back to the fact that all of these involve many different pieces. So determining initial feasibility is not just technical feasibility, is the mass going to fit on the lander? But it also includes the desirability of the customer. Is the mission worth doing? And the economic viability. Do we think that it can be done programmatically within cost and schedule? And it's really important to find that area of selectability where all these pieces can come together and then you ultimately have this successful mission. And I'll note here that one of the key challenges that we oftentimes work with PIs on missions is helping them to understand that the customer is not yourself, it's not the proposer, but it's the purchaser, it's NASA, right? You need to think about what does NASA want when you're thinking about what the customer wants, because they're only going to fund something that they want and you want to give them, what they're looking for. So what we found is that when it comes to determining initial feasibility, what's very useful is to think about your boundary conditions. So I was not a fan of my differential equations class, but one of the key takeaways from that class is that understanding your boundary conditions is critical. And once you understand your boundary conditions, then you can understand, where is that area of selectability. So what are the boundary conditions if we look at these three main components? Well, on customer desirability, the boundary condition is going to be what we call the performance floor. That's generally past, current, and future projects. NASA isn't going to do anything that they've either already done before or they are planning to do in the future. So once you understand that performance floor, then you can try to fit into what's going to make it new and something that they're looking for. The boundary condition on technical feasibility is what we call the capability wall. This is oftentimes a size, mass, power, data rate constraint. Your lander is going to have some mass capability that you just can't go past. You're going to have some power, maximum power that's driven by the selection of your power system. So if you can establish that capability wall, then you know what your maximum constraints are on the technical feasibility of the concept. And the boundary condition on economic viability is what we refer to as the cost ceiling, the cost cap. For a competed mission, this is generally pretty easy. Competed missions, NASA comes to us and they say, you have $500 million and you can't go any further than that. Okay, it's easy. That's the cost cap. For other missions where there's not a specific proposal call, it can be a little bit more difficult. You've got to kind of think about what is NASA looking for this mission? How much would they reasonably pay for it? But ultimately, if you can establish those boundary conditions, now you've framed that selectability area and you can fit your concept within that. So let's go back to our example, our Lunar Polar Volatiles Explorer. This is not an exhaustive list, but I wanted to provide some examples of boundary conditions for this mission, which are hopefully illustrative to you. So thinking about our rover mission that's going to go explore volatiles and customer desirability, oftentimes it's useful to look at past missions. So we know that the L-Cross Impactor mission confirmed the existence of water ice at the lunar South Pole. So that probably tells us that it's not good enough for our mission just to show that there's water there. We already know that. So NASA is not going to want to pay money to do that again. We also want to look at future missions. So there's a mission called Lunar Trailblazer. That's an orbiter mission, a small sat. They have one science objective to determine the form and abundance of ice, bound H2O, and OH in permanently shadowed regions. So that tells us that doing another orbiter mission, unless it does something substantially different than Lunar Trailblazer, is also probably not going to fit within the customer desirability. So those establish some boundary conditions on what NASA is looking for. For technical feasibility, oftentimes it's useful to look at what the capability is of your delivery system. So, Blue Moon has advertised multiple metric tons of payload delivery capability. So that tells us that we probably don't want to make a 10,000 kilogram rover. It's just not going to work. It's also oftentimes useful to look at prior missions. So for instance, the Curiosity rover was about 900 kilograms, 80 kilograms of that was science payload. We can derive a payload mass fraction that we can then use to estimate, well, for a theoretical rover that weighs some mass, let's say 1,500 kilograms, the maximum payload mass is likely around 133 kilograms. And again, none of these are perfect numbers, but it's helping you to kind of frame your thinking of what's possible. And finally, on the economic viability, again, this one can be the trickier one. But in this case, we know that the New Frontiers program that NASA puts out every couple of years has an established cost cap of about $850 million for phase A through D, not including the launch vehicle. So that kind of gives us a target that we probably want to go for a mission like this. That's kind of NASA's willing to pay that much money for these types of planetary missions. So once you've established these boundary conditions, then the question is, do basic calculations or analogies to other projects demonstrate that you can fit within those boundary conditions? And again, you're not looking for the perfect answer at CML2, but you're looking for an answer that's good enough to give you confidence that you should move forward because you've proven that initial feasibility. Okay, so we know that we have a great concept. We think that it's going to be feasible based on our initial feasibility checks. So now we move on to CML3, which is the last CML that I'll talk to you about today. So CML3 is the trade space. So at this point, you've got an idea, but before you dive really deep into, this is going to be an RTG powered rover with 6 wheels and a 2-meter drill. And before you start getting into that level of a point design, it's worth your time to spend some time exploring the trade space. And really, what you're doing is you're exploring that region of selectability. And it's important to just to highlight again, to stay in that region of selectability. Oftentimes we see groups that like to explore up here into what's desirable and what's feasible. But then they completely miss the economic viability. You could have an awesome mission that's technically feasible, but if it costs $10 billion, it's probably just never going to be selected. So you want to have some spaced waypoints, walk through the selectability space. And oftentimes we like to help people to put together what we call, their box. And the box generally has a number of boundaries. Again, going back to those boundary conditions. And within those boundaries, there's all these different pieces that you can move around, and they're all connected to each other. You can have a really low cost mission, but it might not do too much science. But because it's really low cost, your strategy is that it has a really good chance of being selected because that NASA is kind of trying to watch their budget this year. Or you could have a really, really innovative mission that really pushes the cost boundary, but then that's going to put more onto your strategy because now you've got to be able to make the argument that it's worth that larger cost. These are just some examples, but really the point is that you've got all these different knobs to turn. And what makes a concept powerful is if you're able to trade all of those dimensions and turn all of those knobs within your box. And it's worth it to really think about those things early on. Again, before you dive really deep, because you don't want to end up looking at something, making some decision that ends up not working, spending a ton of time on your design, and then having to go back because you didn't really think about all the pieces early on. So that's why it's so important to explore the trade space. So what's our example? So given our lunar example, here's a couple of trades that you'd probably see for a rover mission like we've been talking about. And the point here is that these trades can get kind of complicated and they can involve a lot of different pieces. So for instance, imagine a power, a concept of operations, and a how to access the subsurface trade. You have your ConOps where do you drive really far and cover only a few sites? Do you stay in one area but cover lots of science sites? Then you have your power. Do you want to do a solar plus battery? Are you able to drive into the sunlit regions, charge your batteries, drive into the PSR, and then be able to get back out again so that your mission doesn't freeze? Do you need to just go right for an RTG so that you can have power in darkness? Are there other options like power beaming? But then what does that do? Because now you need a beaming station. I mean, these are the trades that you want to be thinking about. And then subsurface access. How are you actually going to access the surface? I mean, you could use a drill, you could use a scoop. There's some new designs for pneumatic systems. But all these end up being really tied together. I mean, if you want to drive really far and cover a few sites, oftentimes driving can be one of the largest power drivers. So maybe that requires an RTG because you don't have time to stop and charge your batteries. But maybe the RTG has a problem because it's a big cost driver. So you actually can't do that. So you've got to look at a solar option. But then how does that solar option flow all the way down to how you're going to access the subsurface? Because maybe you can only do pneumatics if you're solar because pneumatics have a really low power draw. So ultimately, these trades can get quite complex, but it's worth thinking about early. And again, I know this is just one example for the rover mission we've been talking about. But the point here is that really these trades can build off each other. They can also, they often involve multiple dimensions, cost, science, engineering in this case. But thinking about all of them is really important early on in your concept development. So once you've explored the trades, this is just a peek into CML4 at JPL. Once our concept teams have, formulated their idea, they've proven initial feasibility, they've done all of their trades. So, they have a concept where in our rover case, let's say it's going to be a RTG powered rover that's going to drive far to a few sites and use a drill. They have their concept all put together, all formulated. Then they come to us at Team X and Team XC. Team XC is the team that I lead, more focused on small missions. Team X is focused on larger missions, but both really operate in the same way. It's a lot like A-Team, where we get a bunch of people in the room, although in this case on WebEx, because we've been working remotely for the last year. These pictures are all pre-COVID. And we get all these people together. We get subsystem experts from all the classical spacecraft subsystems like power, thermal, attitude control, mechanical, et cetera. And we all work together over the course of about a week. We have a connected spreadsheet data sharing system that allows the experts to share data between themselves to very quickly come up with a design. So for instance, the science chair can tell the instrument chair that they want to take a few extra measurements. The instrument chair can put in, okay, we're going to need more power at this point because we're going to have to turn on this instrument. That flows to the power chair so that they can resize the battery. That flows to the mechanical chair so that they can add more structure mass to hold the batteries. This connected system of having people together with a way to share data is really what allows us to come up with point designs very quickly. And when a team comes out of CML4 at JPL, they've got now a design for this rover, in this case, with a mass list that goes through each subsystem. They've got a concept of operations that goes through all the different power modes. They've got a mission cost that goes all the way from phase A through phase E operations. That all really gives them that concrete point design that, again, then they go to the later CMLs to actually, hopefully write up as a proposal to NASA to become a mission. So I just wanted to highlight that to kind of give you an idea of, once you have your idea at JPL, at least, how we then put that into the point design of CML4. Okay, so just to wrap up here, and again, now that I have the plot up again, so yeah, once you get to CML4, now you've got your design that you're still only halfway done. It then normally goes at JPL to a more dedicated team to really refine the concept and ultimately get to that PDR at CML8 and move over to implementation. So just a couple of thoughts I wanted to leave you with. Hopefully this has been informative to you in understanding that formulation for a mission can be thought of as a process. There's steps that you can follow. Each step's a little bit unique depending on what your mission is, but walking through the steps is important, and not skipping a step is important. At JPL, we use these concept maturity levels to help define those steps. You can use these, just a little bit of the secret sauce that I'm sharing with you. You can use these steps in your concept development to ultimately, have a successful concept that'll move forward. Okay, so I think that's just about right on time. I have sent these slides as a PDF. You're welcome to send them out to all the students. Here's the contact information for myself, as well as the leads for the other teams within the Foundry. Like I said, I lead Team XC, but we all work really closely together with the other leads. So thank you very much. I really appreciate the opportunity to talk to you all today. This is a really interesting class. I wish I had the opportunity to take a class like this when I was at school. So you're quite lucky. And it's a pretty exciting time for the space program, especially for lunar exploration and everything that's going on in that area. So have fun with it. And I'm looking forward to the next hour and a half and participating in some of the breakout groups as well. So
Cool.
Thank you very much.
Thank you so much, Alex. Thank you for joining us and for this great introduction to mission formulation. It's really exciting to have just a peek into what's going on at JPL. Before we go into the breakout groups, though, I wanted to give the students a chance to to ask you some questions, if that's all right.
Sure, sounds great.
Cool. So feel free to unmute and just ask any questions if you have them.
Thanks, Alex, for that presentation. It was really awesome. I'm kind of curious, in the 5 years you've been working with sort of the formulation team at JPL, has there been any missions that you've kind of had to have pried from your fingers that you kind of wanted to keep working on further down the process? Or are you pretty happy just moving from one formulation to the next?
So I think you're asking for me personally, or more generally for missions that we see come through.
I was meaning like yourself personally, but in general it's fine too. Just sort of, I'm curious if there's any particular missions or any examples that kind of, has really grabbed people's attention.
That's a great question. Let me scroll up back to the chart that shows some of my favorite missions. So, like I said, at JPL, we generally work on something like 25 mission proposals a year. We don't win all of those, but we've been pretty successful. And those mission proposals can be anything from a $1 billion big mission down to a small sat for $5 million, like a little CubeSat. And I'll give you an example. So one of my favorite missions that I actually had the chance to work on all the way from idea, now they're into implementation, is this one SphereX in the top right corner. It's an astrophysics mission, a space telescope. And for me personally, I actually really enjoy, this up to CML8. I'm not the type of person that really wants to, go and machine the parts and bolt it all together. I like the ideation part, coming up with the idea. For me personally, I haven't really felt a tug to go and, continue on with these missions, because I kind of like to go come up with the next thing. But that's not true for everyone. So while we have leads of the Innovation Foundry, really there's a huge team behind the Foundry, and it covers all of JPL. We bring in experts from all across the laboratory. Like I said, we have over 6,000 employees that cover just about every space field you could think of. And we bring these experts in to help with the formulation of these concepts. And a lot of them then move on to the implementation of the concept too. So what I didn't touch on here in the maturity of a concept is the fact that we're also really building the team to then finally implement the concept. Like I said, a lot of those people, they continue on with it, they launch, and then they come back to step one. So for me, at least, I kind of enjoy the process of, formulating the missions and helping them through that process. But for a large portion of the lab, yes, we're really helping to build the team. And a lot of those people do continue on with the missions. That's a great question.
Hey, Alex, thanks for the presentation. My question was around, so when you're formulating a mission for maybe something smaller and you're thinking about how it can be consolidated into, a larger mission with multiple different objectives, at what stage does that happen? And how does that kind of process of putting together smaller missions into, one rover or one mission work?
That's a great question. So that happens a lot. And so the example I gave you today was for, a pretty big rover mission. But a lot of times what we're working on are concepts for, instruments on a larger mission. A great example would be the Mars helicopter that, had to be part of the Perseverance mission. And the process for formulation of, whether it's a payload or a small flight element or something like that on a larger mission, it's really the same in the end. You still need to come up with the cocktail napkin idea. You still have to do initial feasibility. You still have to do the trade space. But your strategy, your boundary conditions, those are all going to change a bit. So for the helicopter, for instance, rather than the boundary condition on technical capability being, how much total mass can we get to the surface of Mars, it became how much extra mass does Mars 2020 have to hold this helicopter? And once you establish, and that's just one example of mass, but it's a good example. Once you establish that boundary condition, you don't forget about the rest of the rover, because obviously there's a lot of details about getting yourself implemented into the rover. But from the initial putting your concept together perspective, those types of boundary conditions help to frame your thinking. And the helicopter team can then not get too worried about, all the details about, how are you going to interface the battery charging electronics with the rover to make sure that there's not a short that could damage something on the rover. Yes, that's all detail that has to be worked out. But in early formulation, it's all about establishing those kind of key boundary conditions that give yourself the box to then, in the helicopter's case, design within. So the process is similar. You just have to think about it in a little bit of a different way if you're doing a smaller piece of a larger mission versus, an entire large mission. That's a very good question.